Good morning. My name is Jazeem Abdul Jaleel. I am a PhD student from the University of Minnesota. Today I will be presenting the paper Scalable Load Balancing in the Presence of Heterogeneous Servers by Kristen, Gardner, Alexander Wickeham, Sherwin, Doroudi, and myself. Let's begin first by understanding the title. We are working on a load balancing problem. Load balancing refers to efficiently distributing incoming network traffic across a group of servers with an objective like minimizing expected response time, which is the average time a job spends in the system after arrival till its service is completed. Our work addresses load balancing in computer systems. For companies like Amazon Web Services, improving system response time would amount to significant increase in profits. Hence, due to its importance, there exists a vast literature on load balancing. Bulk of the literature addresses systems where the dispatcher has complete information of the state of all its servers at all times and when the servers are homogeneous. That is, they have the same job processing speeds. In such systems, we know that join the shortest queue policy performs best in minimizing mean response time when the service times are independent and identically distributed with non-decreasing hazard rate. However, what we see in practice are not systems where server speeds are all the same, but they are different. Systems consisting of servers with different speeds are called heterogeneous server systems. Now the load balancing task is quite different from earlier. We may want to balance effectively how the workload is distributed across both the fast and slow servers. In literature, it is also termed as the slow server problem. And the best dispatching policy is found to be of a threshold type, where we would want to send a job to a server only if the number of jobs in other servers is above a particular number. For systems with few servers, it is easy for the dispatcher to have complete information of the state of all servers at all times. In applications like cloud computing, we make dispatching decisions for systems with many servers. The task of keeping continuous track of the state of all servers is now difficult and costly. The previously studied policies may not be implementable here. We need a different class of policies to address such systems. This is the scalable load balancing problem. For scalable load balancing problems in homogeneous server settings, there are several power of D policies in literature. Here, instead of keeping continuous track of the state of all servers, at each job dispatch event, we check the current information of D random servers and then use it to select the server to dispatch the job to. In our work, we study scalable load balancing in systems with heterogeneous servers. We develop new power of D policies for this setting and study their performance. We begin by presenting our system model. We then explain our new proposed policies and present an important stability result. We briefly mention the analytical techniques used to study system performance, and finally compare its performance against those present in literature. Let's now proceed to define our model. We have a system with k servers, with each server having its own queue. Qf is the proportion of servers that are fast, and hence the number of fast servers, kf, will be k times qf. Similarly, qs is the proportion of servers that are slow, and the number of slow servers, ks, will be k times qs. We have Poisson job arrivals at rate k times lambda. On job arrival, the load balancer randomly checks df fast servers and ds slow servers for server information, and then decides on the server to send the job to. We introduce two policies that the load balancer can implement. Join idle queue df-ds policy that uses only idleness information of servers for the job dispatch decision. And join shortest queue df-ds policy that uses server queue length information for the job dispatch decision. Next, let's define the two policies, beginning with the join idle queue df-ds policy. Under this policy, on job arrival, the job dispatcher randomly checks DF fast servers and DS slow servers. If there exists an idle fast server among them, the job begins service on one of them. Here is an illustration of this when DF and DS is equal to 2. Say the job arrives and the randomly queue-read fast and slow servers are as shown in the figure. Since there exists an idle fast server in the queue, the job will be dispatched to it. Now, if all the fast servers are busy and there exist idle slow servers in the queue, the job is dispatched to the idle slow server with probability PS or to a random queue-read fast server with probability 1 minus PS. Here is the illustration of this. Say the randomly selected fast and slow servers are as shown in the figure. We see that all the fast servers are busy here, and there exists an idle slow server in the queue. The job can now be either be dispatched to the idle slow server, which happens with probability PS, or be dispatched to a random fast server in the queue, which happens with probability 1 minus PS. Now, if we get all the servers to be busy in the queue, the job is dispatched randomly to one of the selected fast servers with probability PF or randomly to one of the selected slow servers with probability 1 minus PF. Below is the illustration of this. Say the randomly selected fast and slow servers are as shown in the figure. We see that all of these servers are busy. Now the dispatcher can either send the job randomly to one of these fast servers, which happens with probability PF, or send the job randomly to one of the slow servers, which happens with probability 1 minus PF. We have now completed defining the join the idle queue DFDS policy, and will move to the join the shortest queue DFDS policy. Join the shortest queue DFDS policy will differ from the join the idle queue DFDS policy only at instances when the dispatcher decides to send the job to a busy server. Under the join the idle queue DFDS policy, the selection of the busy server in the queue was random. However, under the join the shortest queue DFDS policy, the job will be sent to the busy server with the shortest queue in the queue for that particular speed. Let's better understand this using illustrations. If the queue has an idle fast server, the JSQ DFDS policy will perform exactly the same as the JIQ DFDS policy and dispatch the job to the idle fast server in the queue. If all the busy fast servers were busy and there exist idle slow servers in the queue, the job is either dispatched to the idle slow server with probability PS or to the busy fast server with the shortest queue with probability 1 minus PS. If it were the join the idle queue DFDS policy, the job, if decided to be sent to the fast servers, would have randomly selected one of the queue-read fast servers. However, under the join the shortest queue DFDS policy, the fast server with the shortest queue would be selected for dispatching the job. Similarly, if all the queue-read servers are busy under join the shortest queue DFDS policy, the job will be dispatched to the queue-read fast server with the shortest queue with probability PF, and to the queue-read slow server with the shortest queue with probability 1 minus PF. We have now completed defining the join the shortest queue DFDS policy. One major result of our work is the stability of our proposed policies. By stability, we refer to the property that each server experiences an average arrival rate less than its service rate. which is a necessary condition for achieving finite mean response time for our system. Under both the proposed policies, as long as both df and ds are greater than or equal to 1, there exist choices of df and ts such that the system is stable for all lambda less than the average processing rate of the system servers. This is a significant result because, as we will show you later, many power of t policies in the literature developed for homogeneous server systems need not be stable at high loads in the heterogeneous server settings. We used mean field analysis to help us calculate the mean response time for our policies. Since we are addressing the problem when the number of servers in the system is very large, we use the asymptotic independence assumption that each server can be considered to function independently of the others, having the same limiting probabilities. Though both our policies are defined very similar to each other, the approach used in calculating the expected response time is very different for both. For the join the idle queue DFDS policy, we used a tagged server approach that helped us calculate the expected response time with any general service time distributions. For the join the shortest queue DFDS policy, we solved differential equations to obtain the limiting state probabilities of the servers when service time follow exponential distribution. Given the system parameters and df and ds, what we have is an optimization problem. To determine the optimal probabilities, pf and ps, that will help us minimize the mean response time for each of the policies. In practice, instead of fixing df and ds, we would be fixing the sum of them, df plus ds. In our paper, we compare the performance of the proposed policies against the following policies in literature. Join the shortest queue T. Here we randomly queue read servers and send the job to the server with the shortest queue. Shortest expected delay D, where we randomly queue read servers and send the job to the server with the shortest expected delay. Weighted join the shortest queue T, where we queue read servers with the probability that a server of a particular speed is queue read is proportional to its speed, and then send the job to the server with the shortest queue. Join the idle queue, where we dispatch to a random idle server if there is one, else to a random busy server. Note that unlike the other listed policies, join the idle queue is not a power of D policy. Here the dispatcher is continuously aware of all the idle servers in the system. In this figure, we plot the mean response time against system load for different policies. The percentage of fast servers is low and the ratio of fast server speed to slow server speed is high. Note the apparent instability of join the shortest queue 4 and shortest expected delay 4 policies at high loads. This occurs because the slow servers are getting overutilized here. By theorem 1, we have joined the idle queue 2-2 and joined the shortest queue 2-2 policies to be always stable. At low loads, the join the idle queue policy has high response time compared to our proposed policies because they do not effectively utilize the fast servers as they should. When the ratio of fast server speed to slow server speed is low, we see that our proposed policy underperforms at high loads. This is because there is little value in utilizing the speed information here. The main takeaway of our numerical results are: our proposed policy guarantees stability whenever the arrival rate to the system is lower than the system's job processing rate, which is not true for many policies in literature. The best dispatching policy will depend on the problem parameters being addressed. To conclude, in our paper, we introduced and analyzed new scalable power of D load balancing policies for heterogeneous systems. We presented many results pertaining to the proposed policies. Establishing the stability of these policies is one of our main results. We identified parameter settings that tend to favor our policies to that present in literature. We are currently working on a more general framework, addressing systems with multiple server speeds and using a more general queuing and dispatching policy.